Please give a warm welcome to Ann Cui, Jatin Kataria, and Salvatore Stolfo.
Okay, good morning. Hope everybody's properly caffeinated. We have a lot of information in this slide, in this talk. So, my name is Ang Cui. This is Jatin Kataria. We're from Columbia University's Intrusion Detection Systems Lab, and we're going to talk about recent advancements in reliable Cisco iOS shellcode and rootkit design. This is a turbo talk, so I'm going to talk with maximal turboness, and we're not going to have time to cover prior works, but here's a list of great works done by other folks in this area. Let's talk about motivation. Why do we care? Depending on who you ask and when you ask it, Cisco has anywhere between 30 to 80% of the market share as far as high-end enterprise-level networking gear goes, which means Cisco iOS runs a large portion of our global networking infrastructure. And for the attacker, that means iOS is a high-value target. But for the attacker, things get even better, because iOS is essentially undefended, meaning unlike our general-purpose computer counterparts, right, Cisco iOS has no host-based defense mechanisms to speak of, no antivirus, no malware protection mechanisms. And for the attacker, things get even better than that, because iOS is essentially unmonitored, meaning now we do have network-based intrusion detection systems that can monitor the uptime, system utilization, behavior pattern of our networking gear, but none of these things have real internal view of what's going on inside iOS. Which means if you're able to manage to get a piece of malware running inside iOS, and you manage to not use an absurd amount of resources or crash the box, chances are your presence will be very difficult to detect. And of course, Cisco iOS is just a piece of software, and like every other piece of software we're going to talk about this week, it is vulnerable to exploitation. And in fact, we've seen a lot of vulnerability reports, proof of concept shellcodes, and even rootkits for Cisco iOS. But the big question is, why have we not seen the same level of large-scale exploitation of iOS and other embedded systems as we've seen for general-purpose computers? And the answer really comes down to the problem of software diversity. Okay, as FX and others have pointed out, there are something on the order of 300,000 different iOS images in the world, in the wild, and these images vary greatly as far as memory layout is concerned, which means if you design a piece of shellcode to work with a specific version of iOS and you try to use that shellcode on an unknown iOS device out on the network, the memory layout of this victim device will be different from what you expect, and chances are your shellcode is not going to work, and you can probably just end up crashing the device altogether. And in my opinion, this is the last real obstacle that stands in the way of practical, reliable, large-scale exploitation of Cisco iOS and other embedded device systems. And this is the obstacle that we're going to overcome in this talk in the next 17 minutes. So when we talk about iOS diversity, we're really talking about binary diversity, diversity of the firmware. We're not talking about functional diversity, right? So if you think about it, a router, a switch, regardless of the software revision, they have to do some pretty predictable things. So in a sense, they really represent what I'm going to call a functional monoculture. And here's a good example of what I'm talking about. Regardless of software version, on any iOS device on the admin interface, if you put in the enable command and you put in the wrong password 3 times, a very predictable string is going to come out. It's going to be either bad secrets or bad password. Now, if we have a vulnerability that gives us arbitrary memory modification, memory corruption, we know the exact location of this function inside iOS, we can then go ahead and just patch this function and change the way the router handles authentication, and that's going to allow us to put in a persistent backdoor. But this is exactly the problem of the diversity issue, right? We have no idea for an unknown iOS device the location of this function in memory. In fact, we don't even know the location of this bad secret string. The only thing we do know is that this string does exist in every iOS image out there. So what do you do in this case? This is something FX talked about 2 years ago. The general strategy is you use some functional invariant, in this case, the function and the string, right, that it prints out, and compute some feature at exploitation time to resolve the binary target for this unknown iOS image. And in this case, the memory location of the function that handles authentication. Right, so in this case, it's a very simple 2-step process. First, you scan through at exploitation time the data section looking for this bad secret string. Once you find that string, you scan through the text section, right, looking for a reference to that piece of memory. And when you find that reference, then you would have found the function that handles authentication, right? And then this is where you can go ahead and patch the function and get persistent backdoor. Now, this works, but there are some issues with this approach, right? We do have to compute this pretty complicated 2-step process at exploitation time. And if you're doing this on a busy router, that's going to mean there's a good chance your shellcode will be caught by what's known as the watchdog timer. Right? When this happens, your shellcode will be terminated, your process will be terminated, your attempt will be logged in great detail in traceback, both in console and syslog and core dump, and your attempt will fail, and chances are you can even potentially crash the router that you're working with. But there's actually even more subtle problem than just this. Now, suppose our shellcode does execute correctly and we're able to put in a persistent backdoor. That means we already had some vulnerability that allowed us to have arbitrary memory corruption. But the fact that we don't know what the internal memory layout of this iOS image is prevents us from making more modifications to this iOS device, even though we could. And without solving this diversity problem, we're really stuck at this level of exploitation. So that was 2 years ago, and this is now. We're going to show you a new shellcode that we designed that I'm going to call the interrupt hijack shellcode. Specifically, we're going to kill 3 birds with 1 stone with this new design. First, it's going to be faster. Instead of this 2-step process, we're going to do just a single step process that's going to scan through the text section of the router at exploitation time. Second, we're going to be stealthier. Now, suppose we do have a backdoor that allows us persistent root level access to this router. You're going to need to access that backdoor through some persistent TCP connection. Now, that's a connection that's going to be logged and monitored by traditional intrusion detection systems. And that's just a piece of evidence that other people can use that can alert others to our presence. In contrast, the interrupt hijack shellcode, you're going to see in a few slides, uses a wide spectrum of different types of protocols that are unrelated, that are process switched. Specifically, we're going to use the payloads of these process switch packets to construct a coherent command and control channel. Doing this will, because these packets are unrelated, traditional intrusion detection systems will have a harder time constructing our command and control channel, so it'll be stealthier and more difficult to detect. And specifically, the command and control channel we're talking about also is bidirectional. So we can use this to exfiltrate information back to the attacker in a stealthy way. And that's going to be very useful, very important when we try to actually solve this diversity problem. And lastly, we want to have more control. Now, if we put in a persistent backdoor, we're still stuck with interacting with the existing iOS shell, right? We get level 15 privilege on the router, but we're not able to do anything more than just manipulate the router through iOS commands. But if we're able to put in a rootkit on this router, right, we already are operating on the supervisor mode on the CPU, which means we can potentially read, write, execute any piece of memory on this router, right? And if we solve the diversity problem and figure out exactly what the memory layout of this device which is compromised is, we can really take advantage of that fact. So here is how the interrupt hijack shellcode works. It works in 2 stages. First stage, it unpacks the second stage at a predictable location in memory on the victim router. Then it's going to scan through the text section once of the victim device, looking for the exit points of all the interrupt handlers it encounters. Once it finds that, and this is easy to find on the MIPS platform because that's just a 32-bit fixed pattern. The opcode is ERET, which stands for exception return. Once we find these ERET instructions, we're going to put hooks pointing to our second stage payload. And as a last step, we're also going to calculate a hash of all of the addresses of all the ERET instructions that we've just located. I'm going to call this thing the fingerprint, and this is going to be very important when we try to solve the diversity problem in a few slides, so keep in mind that we have this and think about why we're doing that. Now, once the second stage payload is active in the router, right, we've done something pretty cute. We've just escaped the tyrannies of the watchdog timer forever. Now, our second stage payload can now execute forever on the CPU without being caught by the watchdog timer, and here's why. So imagine your Cisco router, you have hundreds of different processes running, and you have interrupts firing off at all times. Each time any of those interrupts fire off, the appropriate interrupt handler is called, right? But before the handler returns control of the CPU back to the original process context, we get to now execute a small burst of our second stage payload. And by small burst, I mean anywhere between a few hundred to a few thousand instructions, right? Because we execute in such small bursts, in the context of many different interrupt handlers, this is not something that the watchdog timer can ever pick up on. And in fact, our CPU load for our second stage shellcode is going to be distributed evenly across all of the iOS processes inside this environment. So a network administrator can come in and pinpoint a specific process that has an abnormal elevated CPU utilization because our load is going to be distributed equally across every piece of code in the system. Now, this is our low-level second stage rootkit that's going to run forever on the victim device, and it's going to allow us to, oh, by the way, didn't tell you what the second stage does. The second stage is going to continuously scan through the IO mem range of our victim router. Specifically, we're going to look at the payloads of process switch packets, and we're going to look for a special 32-bit magic pattern that's going to indicate a command and control request. And that pattern is going to be followed by one of three possible commands: load code, execute code, or exfiltrate data. Now, this is our low-level second stage rootkit that's going to give us arbitrary access to any piece of memory inside the iOS environment. We're running inside the interrupt handler, we're running at supervisor mode on the CPU. But we still, at this point, haven't solved the diversity problem. We can make modifications to any part of this router, but we have no idea what the memory layout of our victim device is. So this is where the fingerprint that I just talked about comes in. All right, first I'm going to show you how we exfiltrate this fingerprint back. Then I'm going to talk about why this fingerprint solves the diversity problem, and then I think it'll be pretty clear. So I, the attacker, generate a regular old ICMP echo request, a ping message. But inside the ICMP payload of this ping message, I'm going to put in my 32-bit magic pattern, followed by the exfiltration command, followed by the operand that says I want that fingerprint exfiltrated back to me. I send a ping to the administrative interface of my victim router that already has the second stage rootkit running. Usually, right, if the router answers pings, it's going to take this ping message, it's going to copy it into the IO mem of this router, it's going to put it on the RX queue, and because it's punted to CPU in Cisco speak, the CPU is going to come along, parse the packet header, and generate a corresponding ICMP echo response header. It's then going to take the ICMP payload from the request, copy it to the response packet, put that entire packet on the TX queue, right? And then this outbound packet would be then sent out through some physical interface on the wire. But because I have my interrupt hijack shellcode in place already, and because I did put in the 32-bit magic pattern, my shellcode is going to come along, see this as a command and control request, and it's going to service the exfiltration command. The way we do this is really simple. We're simply going to wait until the router constructs this ICMP echo response, and we're going to wait until it puts this packet on the TX queue. But before this outbound packet gets transmitted on the wire, my interrupt hijack shellcode is going to come along and modify the ICMP payload, okay, and replace that content with the exfiltrated data that I want to get back. So this new modified payload is going to be sent out, it's going to be placed on the TX queue, it's going to be sent out as usual, and this ping response is going to come back to me, the attacker. I simply parse the ICMP response, and inside the payload, instead of my original request, I'm going to get this 32-bit fingerprint that I just computed as part of my first stage shellcode. Now, this is the fingerprint that's going to allow us to make a positive identification on exactly the hardware platform and the software version of this victim device. And Jaden's going to start running some demos in a. Oh, sorry. And now, let's take a step back and see why this fingerprint helps us solve the diversity problem. If I were to ask you to solve the address-based randomization problem for the general case, right, that's a difficult thing to solve. But if I were to scope down the question and ask you to solve ASR for which there are only 300,000 possible permutations, right, then this all of a sudden becomes a pretty trivial thing to solve. All you have to do is simply compute some feature at exploitation time to figure out which one of the 300,000 permutations you're in, right? Consult a lookup table of some sort, and then figure out from that exactly the memory layout of this specific instance that you're working with. And this is exactly how we're going to solve the iOS diversity problem. We're going to build a lookup table. This table is going to contain one row for every iOS image in existence, and we're going to compute in an offline fashion the fingerprint, right, or the address of all the ERED instructions hashed for every image in existence. And then we're simply going to make a lookup, and that lookup is going to give us positive ID on exactly what hardware and software version our victim router is. So Jaden's going to show you some really cool demos. We're going to show you this whole thing working from beginning to end on a physical 1841 Cisco router. We chose this because this is the only one that fits in my backpack. We've tested this thing on 7200s and other hardware platforms too. So in theory, this should work on every Cisco router out there. But here's a four-step generalized process of reliable exploitation of iOS, unknown iOS device for out on the network. First part, I trigger some vulnerability, and as the part of my initial attack, I sent along the 400 bytes that represents my first stage and second stage interrupt hijack shellcode. Once that executes, right, the first stage unpacks the second stage starts answering my command and control request. I make immediately a request for exfiltration of the fingerprint. And I'm going to do this through a specially crafted ICMP ping message. Once I get back the fingerprint, I make a query to my offline database that contains fingerprints for every known iOS image I know about. And at this point, I make a positive ID. I find out exactly what hardware and software version I'm working with. Now, once I know the iOS version, and once I have the second stage rootkit that gives me arbitrary read, write, execute, right, we've solved every piece of this puzzle. We can now start using the same second stage rootkit to upload device or version specific third stage payloads to change the behavior of this router in any way we want. So Jaden's going to start showing you how that whole thing works.
Hi guys.
So first we're going to...
This is a 1841 router.
Right, so first we're going to show you guys how to load our first stage and second stage. We introduced a really trivial vulnerability inside the show CDB command, just so that you guys can see this thing loading. But the entire payload is really just 400 bytes, and it can be passed along to any vulnerability. So now, once the second stage is active, Jaden's going to, on the bottom screen, he's running a script that's parsing ICMP messages. And he just sent a special program that we wrote to generate ICMP messages for exfiltration of the fingerprint. And now once we did that, right, as soon as it comes back, we make a lookup, right, and this now shows us that we're working with a C1841, and what is the software version?
It's 12.4 version. IP-based MZ 12.4.
So that's the exact software version of iOS our victim router is running. Now from here on, we have every piece of... Sorry. So now we can make arbitrary read, write, execute to any piece of memory on this router, and we know exactly what the memory layout is, so we own this router completely. To show that happening, first we're going to show you that we can change, let's say, the show version command of this router. This is what it usually looks like. Now Jaden's going to send a ping packet with a command and control request, and now, ta-da, right? So we're always talking about how we need more cats on the internet. This is how we're going to do it. And also, there's a command that a lot of folks like to throw around that some people think is a security feature. Show sum in iOS calculates the checksum of the memory resident iOS image and compares it to some expected value. So if you start patching iOS like the way we're doing, right, you can see, oh, something went wrong, there's a bug, or you have a rootkit being installed. But this is absolutely just a debugging tool. It is not a security feature. And we're going to show you how easily we can just deactivate that using the same second stage payload. Did that work? Okay, so ta-da, right? So we sent this one ping, and now we've deactivated the show sum. So from then on, right, it's going to show everything's hunky-dory, no modifications being made. And the last thing we're going to show you, just really drive this thing home, is we're going to completely disable authentication on this router, right? So now when Jaden's going to type in the password wrong 3 times, okay, ta-da, the hash mark gives you root on this router, so we own everything about it. Okay, so we win. Now, because our demos have all worked out, this live demo, we're going to make a sacrifice to the demo gods. We don't have time to go into exactly how this is going to work, but this is a remote brick. It's going to physically brick this 1841 router so that it prevents it from booting up iOS after this reboot. The way it roughly works is we're going to overwrite the EEPROM content of the motherboard of this router, so that once it reboots, the first level loader is going to look at the EEPROM and it's going to say, you're no longer running legit, genuine Cisco hardware, I'm going to refuse to reboot, go away. Now, ROM-on upgrade is not going to fix this problem. An iOS upgrade is not going to fix this problem. The only way to revive your router after this happening to you is if you restore the exact EEPROM content of your router, and this information is device specific. Now, I carry around the EEPROM of that router in my pocket, so I can do this demo over and over again. But my question to you, for you guys in the audience who are network administrators, is do you, okay? So maybe it's time to think about backing up the EEPROM of your devices, especially if you have thousands of these on your network. So now, we just send the brick command, we send a reboot command using the same second stage mechanism. And I guess did you do it?
Yeah.
Okay, so the router rebooted. It's going to take some minutes to come back, and It's going to just get stuck here, so let's go back to the PowerPoint. All right, so we don't have time to stare at this router. If you're not convinced, you can come find me afterwards, and you can try all you want to reboot this router. But without the EEPROM value, it's not going to work. So, what's new and exciting in the offensive work area? Okay, so we built a 3,000 image database just as a proof of concept. That's roughly a 1% coverage of all the iOS for devices out there. But for a moderately motivated individual, right, getting the other 99% coverage is really not all that difficult. It will take about 1 or 2 weeks to download all these images from Cisco's website. Calculating these hashes, if you're clever about it, should take no more than just a few hours on regular powered computers. More excitingly, this EEPROM stuff we just showed you, we're currently developing hardware-resident malware that we hope will be capable of hardware-hardware contact propagation. Meaning, if I were able to get malware on a line card, for example, right, the EEPROM of a line card, and if I plug that into a router, potentially I could use that to infect the EEPROM of the motherboard, and from there I can infect iOS devices or iOS images and vice versa and have it propagate that way. On the defensive side, we have a lot of very interesting work going on. We've created a software construct called the software symbiote. This is something that is a software-only solution that can be injected directly into firmwares like Cisco iOS that can protect embedded systems against all of this malicious execution pattern that we just talked about today. The paper that will detail exactly how this defense works is called Defending Legacy Embedded Systems Using Software Symbiotes. It will be published in RAID 2011. That's in September, I think. So that's a very exciting paper. Look out for it. There's a lot of good information there. And using the software symbiote, we've constructed a line of physical Cisco hardware, Cisco routers, that are capable of quietly detecting and capturing real-world iOS exploitation attempts. Right? And we hope to distribute this across the internet to start actually catching real-world exploitation of Cisco routers. And that brings me to my last point. All the defenses that we've tested against have been against the malicious code that we've written or found through proof of concept code from other folks who have done research in this area. But if you or somebody you know have access to real-world iOS malware, we would love to talk to you because I would like to set up some friendly shootout just to see how our defenses stack up against malware we find in the wild for Cisco iOS. So that's it. That's my talk. Please, here's my contact information along with my advisor's contact information. And please check out our website for our ongoing research and publications. And thank you, Jaden, for being DJ demo. Yay, Cisco. All right. Okay, so I have a few minutes, so you there?
So, you guys kind of seems like you sidestepped the issue of diversity in the original thinking.
Yes, exactly, right. And that is a difficult problem, right? And there are some things that you can do about it. So there is an easy way, well, I think an easy way to sidestep that problem, but we haven't exactly solved that last diversity problem. So the question is, how do you get the initial shellcode to execute reliably inside the iOS environment? So that in itself is also a diversity problem. But we're currently working on that. We have some good results, but we didn't have time to show anything mature, but maybe in a few months. Right. No, not at all. So this right here, none of the stuff we're talking about here has anything to do with the Raman version, right? So yeah, we're not talking about that at all. So we're not using Raman to get any of the payloads to execute. We're not using Raman to get the first and second stage interrupt hijack to execute. We're simply just looking for the exit points of interrupt handlers, which is very easy to find because that's a 32-bit fixed pattern, right? There's no operands in that opcode, so you can just scan through memory very quickly and find all of them efficiently. Say again? Right. So once you have that, okay, if you have a good way to get shellcode to execute reliably, then I would say we have a very big problem here, right? Because then it becomes very trivial to exploit these things. So that's a very good point. That's the last problem we have. So.
Is
this only available on iOS but not iOS XR? I assume that
Yeah.
tried iOS XR and it didn't work out there.
We haven't actually looked at XR yet, so we've just tested this on 2800 and 7200s, this 1800 here, for iOS 12.2 to 12.4. So we haven't looked at XR, but that's definitely something we plan to look at in the future.
Is the firmware restore that you're talking about, that DOS attack was done, is that a standard like Cisco support thing that you find on the website, or is that something that contact?
Okay, so the way we wrote EEPROM to this motherboard, we're not using a documented iOS command to do it. We're using our second stage rootkit to do that. Because we're running in the supervisor mode, we're able to make modification to that piece of memory. And the way you restore it is you have to use a ROMON command that's not exactly documented. It's called priv, right? But before you do that, you have to calculate the cookie password, and you can find information on that online. But if you don't know the actual content of the EEPROM ahead of time, it's tricky getting the password, et cetera. So, but yeah.
So have you started building the fingerprint database, or you may share that?
That's a question for Sal, my advisor, I think. Yeah. I mean, we are just doing research. We have no, industrial interest in creating an iOS database. But, I just want to get the point across that doing this is very simple. You just simply have to download these images and, crank it through, any modern CPU, which will take care of it in a few hours.
I'm curious what you think the impact of iOS 15, where they're going to universal is like a simple comment.
Yeah, I think for that part, Cisco can do a lot of things to improve the integrity of their operating system. So in my opinion, what we're dealing with here is just basically a very rudimentary DOS box, right? There's no memory protection here. There's no memory isolation, right? There's really no concept of process. Everything is cooperative multi-threaded, right? Or multi-processing. So, once you start adding in real modern defenses, like memory virtualization, right? That's going to really help improve the security of devices like this. But for now, these, at least up to 12.4, right, there's no such thing, right? So it's very easy to exploit. Which means if you're able to compromise any piece of iOS, even in non-privileged mode, right, you can get supervisor mode on this router and own the entire thing. So that's, I think, a very significant security problem. Right. Okay, so I gotta go. I'm getting the big X. Thank you. Talk to you later.